Again, welcome to the third lecture on analog electronics. So today we are going to see the fixed bias and the design of it. So, so this is the circuit diagram of fixed bias. In this, you can see that RB and RC are connected to a same single source. Single source is used for biasing the transistor. In the previous lecture, we have seen two different sources for biasing base and for biasing the collector. Here we are going to use a single source for biasing the transistor in fixed bias. So in biasing, a single source is used so that the Q point can be kept in the active region. Let's go with the equation. So using KVL, in the input side you can see VCC is equal to IBRB plus VBE. So it is written by the KVL law. So this is an input side circuit. So this is the input side circuit. We are writing this equation from the input side. Okay, the green color arrow shows the input side. Next we are writing the second equation from the output side, that is RC. VCC is equal to ICRC plus VCE. So these are the two important equations that governs the fixed bias circuit. Let's go into the derivation. Before going to the derivation, what we are seeing is the constants and variables. So let's see. So these are the constants used in the equation and these are the variables that is used in the equation. So VCC is the collector voltage that we have used for biasing the circuit, and RC and RB are constants, and VB is always constant if it is working in the active region, that is 0.7 volt. So the variables that may change with respect to the input is IC, IB and VCE. So IC is collector current, IB is base current and VCE is the collector emitter voltage. So now we are rewriting the equation number 2 that is seen in the previous page, that is IC RC is equal to VCC minus VCE. IC is equal to minus VCE by RC and VCC by RC. So this is the equation that is written. So this equation is similar to a straight line equation, right? This equation is similar to the straight line equation. So in which we plot output characteristics of the transistor. In y-axis we are taking IC and in x-axis we are taking VCE. Here you can see it can match a straight line. So this equation is called as the DC load line. That is a very important DC load line. So let's see how we are writing it. That's the DC load line. So the represents this equation represents a straight line with a negative slope. So if it is a straight line, we have to calculate the y-intercept and x-intercept, in which the line cuts in the y-axis and the line cuts in the x-axis. In order to find the y-intercept, we need to make the x-axis 0. So like that, here IC is y and VCE is x. So we have to substitute x is equal to 0 in order to find the y-intercept. So if we substitute 0 in this equation for VCE, the equation becomes IC is equal to VCC by RC. This is the maximum current flowing through the transistor or the collector. Transistor or the output side. So this is what we call the maximum current. The maximum current depends upon the collector resistance. If RC increases, IC max decreases. If RC decreases, IC max increases. So we can design or set the maximum collector current with the help of the RC resistance. Next, if you want to calculate the X interrupt, sorry, we have written it as Y interrupt. So if you want to calculate the X interrupt, we have to put Y is equal to 0, that is IC is equal to 0. So which is equal to VCC is equal to V, that is VCE becomes VCC, that is the maximum voltage. So this is very important, alright. So next we are going to plot the straight line into a graph. Now we have calculated the y-intercept and x-intercept and we are plotting it as the point and we are joining it in the straight line. The red line denotes the DC load line. Red color line denotes the DC load line, right? So from the output characteristics, from the output characteristics you can see the violet color line shows the saturation region of the transistor, and the below violet color lines shows the cutoff region. The in between region is called the active region. So our main motto is, for stable operation we have to keep the Q point in the active region. It must not go into the saturation region and it must not go into the cutoff region. We have to keep the Q point in the saturation region. So we are setting the Q point at the center of the DC load line. Okay, while setting the DC load line we are naming the parameters as ICQ and VCEQ. So we call the Q point as ICQ and VCEQ, that is quiescent collector current and quiescent voltage across collector and emitter. So this is a very important point. So for stable operation, again I am saying, for the stable operation we keep Q point in the active region and also at the center of the DC load line. So this is very important. For any design, if you are going to use the transistor as an amplifier, you have to keep the Q point at the center. So this is the design methodology of a transistor. Okay, so in the next video we will be seeing a simple design problem using fixed bias. Okay, thank you.